Okay, perfect. So, hi, my name is Negar. I'll be your host today. Uh, Thank you for being on time. Okay, so today we have a very exciting lecture. So let me go ahead and introduce our lecturer today. So we have Professor Eli Levinson Falk. He received his PhD in 2013 in Professor Irfan Siddiq's Quantum Neuroelectronic Laboratory. After postdoctoral research at Stanford University, he joined USC as an assistant professor in 2017, and in 2023, he received a joint appointment in electrical and computer engineering. His research focuses on superconducting circuits for qubits, quantum information devices, and detectors with applications in quantum computing, simulation, sensing, and exploring the foundations of quantum mechanics. And today he'll be presenting a very exciting lecture, which is called Drawing Your Hamiltonian, Design Considerations in Superconducting Qubits. So I invite him to mute himself and start.
All right, thank you. Thank you for that wonderful introduction. Can everybody hear me okay? Okay, cool. So of course I need to begin by acknowledging the people who did a lot of the work that you're going to be seeing here, most notably Shanto, who is going to be giving a set of tutorial lectures next week on how to actually use the stuff that I'm going to be talking about. I want to sort of zoom out for a second and say, what do we need if we want to make a quantum computer? Well, we need a quantum object that is addressable, meaning that we can control it. We can control one object, we can couple two of them together, we can measure them easily. Now, we may want some kind of fancier thing, like some kind of quantum control, where we use the state of one object to drive another. We may want joint measurements, but let's just say in general, we need to be able to talk to these things. So that requires coupling. We need systems that we can couple to relatively strong. Now, we also need coherence. Whatever quantum state we put into our quantum object, we want it to only respond to things that we are intending it to respond to, not to any kind of random environmental interaction. So that means it needs to be isolated from its environment. Now, these two things are in tension. If I can talk to my system, so can the environment. In general, anything that couples strongly to my control will couple strongly to a bit of the environment that looks like my control. And so this is really the trade-off that every quantum technology has. Now, there's a third concern here, which can be a little bit separate, which is scaling. One qubit is fun. 10 qubits you can do some really interesting stuff with, but we probably need like millions of these. And so we really need architectures that will scale them. Now, the system I work with to try to solve these challenges is superconducting quantum circuits, and that's why we're all here. And the idea here is that we take a system that ends up having just 1 or 2 degrees of freedom that you can couple to really, really strongly, and everything else is really isolated. And then we just engineer the environment to be particularly clean when it comes to those 1 or 2 degrees of freedom. So here's a picture of a device from my old group in Berkeley, QNL. So can't quite see clearly, but these little double rectangle structures here, those are qubits. These little meandering things, those are resonators coupled to them. And now, in general, what we get with a superconducting circuit is 3 circuit elements. We get a Josephson junction. I'll talk about that in a second. We get a linear inductor, and we get a capacitor. And now we can combine these to form like transmission lines and various different structures. But in general, this is sort of the fundamental building block. And it gives us energy, which if I just write it down as a classical Hamiltonian, we have energy of the capacitors, which is 1/2 the capacitance times the voltage across the capacitor squared. Energy on the inductors, which is 1/2 the inductance times the current through the inductor squared. And then energy on each Josephson junction, which is this Josephson energy here, times cosine of phi, which is the phase difference across the junction. I'll discuss it in a second. Now, this is a classical Hamiltonian. If we want it to be a quantum mechanical Hamiltonian, we do the difficult mathematical operation of putting hats on everything, and now it's quantum. But this isn't really what we're shooting for. What we really want is something more like that. We want some kind of, effective Hamiltonian that looks like, say, a harmonic oscillator or an anharmonic oscillator, and maybe some coupling between them, or maybe it just looks like a spin 1/2. We want to somehow get from this circuit to this effective Hamiltonian. So I'm going to talk about how we do that, but first I just need to sort of introduce some of the basic building blocks here. So let's start with the simplest possible device. Let's take one inductor and one capacitor and put them in parallel. There's a flux through the inductor, or equivalently a phase across it, phi. There's a charge on the capacitor, q. These are canonically conjugate variables, similar to position and momentum, which means that they have a commutation relation where these operators do not commute. They don't commute by an amount I h bar, just like position and momentum. We can relate these to the classical variables of current and voltage. Just the flux is just the current times the inductance. The charge is just the voltage times the capacitance. And we get a Hamiltonian that looks like this. Now, I want to note that here we have a Hamiltonian that goes like these two variables squared, and these variables are conjugate, just like position and momentum. Well, the Hamiltonian that has position squared and momentum squared in it is for a harmonic oscillator. And indeed, this is a harmonic oscillator. This is a quantum harmonic oscillator where the modes of oscillation are charge and flux sort of sloshing back and forth through this thing. Now, in quantum mechanics, the harmonic oscillator has quantized energy levels. So you can only have these particular values of energy. And they're each split by the same amount, h bar omega, where omega is just the classical resonant frequency of the circuit, 1/√LC. If I just make this circuit classically, it acts like a resonant circuit with this resonant frequency. So it's a quantum mechanical object, and it can be a very useful one, but unfortunately, it's very difficult to control. If we try to drive it to, say, drive from this bottom level to the next level up, we have to drive at the resonant frequency between them, but that's also the resonant frequency to drive to the next one and to the next one, and so it's very difficult to control. In order to control it, we need some kind of nonlinearity, and that's where the Josephson junction comes in. Now, a Josephson junction, very generically, is two superconductors with something else in between. And something else can be a huge range of things. But for our purposes, we're going to limit ourselves to talking about what are called SIS junctions, where it's two superconductors with an insulating barrier in between. Here's an actual electron microscope image of a couple of them. So blue here and blue here are these two layers of superconductor. And then orange is the region where they overlap. These are both made of aluminum. There's a little bit of aluminum oxide in between there that you can't see. There's just two of them in parallel. What happens is that current in the form of Cooper pairs of electrons, can tunnel across this insulator without any energy being required. And so it's still a supercurrent. It doesn't dissipate any energy, but it induces some interesting behavior. Now, we represent this in a circuit by just this little symbol X. We give it a critical current, I naught. And the idea is that it's governed by the Josephson relations, where the current that goes through this thing is related to this magnitude I naught times the sine of delta. This is this phase difference across the junction. Really, the way you can think about this is that there's kind of a wave function on the left and a wave function on the right, and they have the same amplitude, but they have a different phase. And the difference in that phase controls how much current goes through. Now that's a DC. At AC, there can be a voltage across it. DC, there's zero voltage, so there's no dissipation. But at AC, there can be a voltage, and that voltage is related to the time derivative of that phase. So as the phase changes, you pick up a voltage, which also changes. Now, we can do some more fancy math known as the chain rule, and just say, well, voltage is proportional to time derivative of phase. Current is also dependent on phase. We can get voltage proportional to the time derivative of current with this other function in front. Now, we have a name for a circuit element that has voltage proportional to time derivative of current. It's called an inductor with an inductance L. So this is a nonlinear inductor whose inductance is given by this function here, And you can see it's got some magnitude, but then it depends on the phase. It depends on cosine delta. This is why I say it's nonlinear, because if you change delta, I also change the current and vice versa. So if I change the amount of current flowing through the inductor, I effectively change its inductance. Now, this is not what happens in a classical linear inductor. It just is an inductance that stays constant. So this change here is the nonlinearity. Now, there's one more building block we need to discuss here, SQUID, a superconducting quantum interference device. There are, again, many ways to make this, but for now, I'm just going to say it's two identical junctions in a loop. These act like a single Josephson junction, whose properties can be tuned by the amount of magnetic flux through this loop. So the critical current, just as the two critical currents added up, times this cosine of the flux divided by the flux quantum. Likewise, the inductance tunes as 1 over that. There's a lot that you can do with squids. This is a vast oversimplification of their behavior. I could teach an entire semester-long course on squids. We don't have nearly that much time. We've got maybe 1 minute. So this is what we're going to treat them as. Okay, so let's do this next most complicated thing. We had our harmonic oscillator. Let's just replace that inductor with a single Josephson junction, or maybe with a squid. If we tune the parameters right, this forms a transmon. This is a superconducting qubit or an artificial atom. So what I'm showing you here is an image of a device from some collaborators at MIT. This cross structure here, this X, makes 1/2 of a capacitor. So that's one plate of the capacitor. All this other metal around it, this ground plane, that's the other half. Right in here, you can just barely see a little loop. That's a squid. The other structures here are from other parts of the circuit, and I'll discuss those later. So if you remember, for the harmonic oscillator, I was drawing this energy, and I said it had evenly spaced energy levels. Now, what I was drawing here was kind of the potential energy in flux coordinates or in phase coordinates, and it was a parabola. And again, that's what you get for a harmonic oscillator. You know, if you think of a mass on a spring, it's 1/2 kx squared. It's x squared. It's a parabola. Well, if I replace that inductor with a Josephson junction, what I get instead is a cosine. And okay, at small values, a cosine looks a lot like a parabola. It's just a Taylor series. But as you go out, you start to notice the difference. And so I get energy levels whose spacing actually decreases as I go up. So I get anharmonic energy levels, anharmonicity. Now, this anharmonicity is typically pretty small, only like 1 to 10% difference in the transition energies between this 0 to 1 state and this 1 to 2 state. I've kind of exaggerated here just so you can see it on the plot. And what this means is that the wave functions that you get are actually pretty close to harmonic oscillator states, and that's kind of nice. It makes all your theory a lot easier. You can use perturbation theory, basically. Now, typically what we'll do is we'll just label these things G for the ground state, E for the first excited, F for the second excited. We already used G, so we got to go to H next. And we'll just say, I'm going to say G and E are going to be labeled 0 and 1, which only have an energy splitting around 4 gigahertz or so. And that's my qubit. And because their transition frequency is different than the transition frequency from E to F or F to H, I can drive transitions between these two without driving the other ones. And so I have a nice isolated qubit. And these are great because they're just very simple. They're very coherent. They're very easy to couple to. So this doesn't couple to anything except electric field, and it couples to electric field very strongly. Basically, the oscillation is charge sloshing back and forth like this, which gives you a very large electric dipole moment. Very easy to couple to. Okay, next most complicated thing. Let's stick a transmon right next to a harmonic oscillator. So I'm just going to couple them with a couple of capacitors. So we've got a qubit here, which is around 4 gigahertz or so. We've got a linear harmonic oscillator, we'll call this a resonator or a cavity. Let's say that's around 6 gigahertz or so. So they're off resonant from each other. And what this does is it makes the cavity kind of act like a filter. The cavity protects the qubit from the external environment by filtering what it sees. And then the qubit, when it changes state, slightly changes the cavity resonant frequency. So you get a cavity resonant frequency, which goes up or down by an amount chi/2, depending on the qubit state, which is represented by sigma z. So what this lets us do is readout. We can send in a microwave tone and look at how it comes out, and it will come out in a different way depending on whether the qubit was in the 0 state or the 1 state. Okay. Now, that was really fast. That was like all of superconducting qubits up through transmons and circuit QED in 10 minutes. So I know there's going to be questions. I will take them at the end. Let's talk about actually building these things. Let's talk about how it usually goes. You come up with some brilliant theory. You're like, oh, I know the perfect Hamiltonian that I need. I even know how to translate it into a set of circuit elements. I know that I need a circuit that looks kind of like this. I need these capacitors and these inductors, and I need them to have these values. And I say, okay, how do I actually make that? Well, okay, I make a best guess. I make some physical layout of a device that I say, I'm going to go fabricate this. And I simulate. I do electromagnetic simulations of this thing to try to predict how it's going to behave. And I update the design, iterate this a few times, finally converge on something that I think is going to be good. I don't personally go into the clean room anymore, but I send my students into the clean room, and they go and they fabricate the device. And then we go and measure this. And I want to point out, both the fabrication and the measurement are expensive in the sense that they cost money and they cost time. This can really take a long time. It can take weeks. And often what happens is we find out that the simulation didn't work in the first place. Something about the simulation was incorrect. So we got to iterate this whole process over and over and over until it's finally good enough, and we get a device that does what we want, and then we write a paper, put it in the archive, and wait for a review or two to tell us how it's wrong. So this is hard. This is a problem. Really what you have is two spaces here. We have a space of Hamiltonians where we say, okay, this is the sort of effective Hamiltonian that describes my qubits and my resonators and all their couplings. This is what I want. And then what I need is to go and map this to some point in design space. I need this to basically map to a particular geometry of a circuit, like an actual physical layout that I'm going to fabricate. Now, this is really hard. In particular, it's a very underdefined problem. You can get pretty much the same effective Hamiltonian with many, many different styles of design. There's other concerns that go into this. Different designs can lead to different coherence. Let's not talk about that yet. Let's just say this mapping is very, very hard. So whenever you're faced with a really, really hard problem like this in science, it's a good idea to step back and just ask what your resources are. What can you do? Well, one thing we can do is we can measure real device behavior, and we're really good at that. We've gotten really good at measuring what a device is actually doing once we've got a physical device. We can simulate the effective Hamiltonian once we have a design file, a GDS file. This is not trivial. In particular, it's really hard to tell whether your simulation actually gave you the right results, but it's at least uniquely defined. A particular physical layout will only give you one effective Hamiltonian. Now, we can do this a lot of times. This kind of computation, it can be computationally intensive, but it can be run on classical computers. And it's generally a lot easier to get classical computing resources than it is to get quantum measurements done. So once you've got your initial investment going, this is not that hard. And then we can, make this stuff scalable and can make it open source as long as you consider we to be Shanto. This is really his expertise, not mine. So how did we go about trying to solve this? Well, what we did first is we take a device that we have physically fabricated that was from this point in design space, And then we go measure it really carefully. And we record all the effective Hamiltonian parameters that we care about. We record the qubit frequencies, we record the anharmonicity, we record all the couplings, and we say, okay, that maps to this point in Hamiltonian space. So this dashed arrow here basically represents that mapping. And then we say, okay, let's go and do electromagnetic simulations on this thing and see if we can get those simulations to actually match. Okay, so we do it once and it misses horribly. We do it another time, misses a little bit less, change something. Okay, it misses the other side. And we basically have all these different parameters that affect the accuracy of the simulations. We just keep turning them up, turning them up, turning them up until finally we get a validated workflow that works well. And importantly, we need to be able to have the same sort of what are called hyperparameters, the parameters of the simulation itself. We need those to work for a lot of different validated devices. For all these different points in design space that we might have fabricated a device, mapping to all these different points in Hamiltonian space that we've measured, we need the same type of simulation to work for all of them. So once we've got that, once we have this validated simulation pipeline, we apply the brute force technique, where we just spam design space. We just make a ton of designs and simulate them. And we simulate them there and there and there. And we just do all this mapping so that we've basically covered Hamiltonian space. So then if you want some point in Hamiltonian space, well, we'll have simulated a nearby one and we know what point in design space gets you there. Now, what does this actually look like? Well, we need to first say, what are the Hamiltonian parameters we care about? So here on the left is an image of the design for a device that we measured in my lab. This was actually made by collaborators at MIT Lincoln Lab via their Foundry program. But we designed it. What you're looking at here is 6 completely independent transmons. These do not couple to each other. And each of them has their own readout resonator. This kind of meandering thing is a section of transmission line that makes a resonant mode. And we're going to represent each of these by saying, okay, this resonator has a frequency omega r, and then this A dagger A is basically counting the number of excitations in the resonator. The qubit has an energy omega q, frequency omega q, and an anharmonicity alpha, and then these operators here sort of represent that anharmonic oscillator. And then they've got a coupling strength G with a charge-charge coupling, which is represented like this. The resonator is also going to have some line width kappa, which you can't actually represent nicely in a Hamiltonian unless you're willing to break some rules. It's really an open quantum system effect, not a closed one, but whatever. We'll just add that in at the end. So we can go measure this thing, basically just doing spectroscopy. And we say, okay, the 0-1 transition frequency, so omega q, is, for say this qubit over here is 4.216 gigahertz. And then we go, when we measure the anharmonicity, measure the difference between the 0 to 1 frequency, the GD, versus the E to F. And we say, okay, the E to F frequency was 153 megahertz lower. Pretty typical value. Then we say, okay, what frequency was the readout resonator? Well, it was at 6.116 gigahertz. Then we measure something called the Lamb shift, also known as the punch-out shift. Basically, if we drive the resonator super, super hard, it kind of just kills the qubit and effectively removes it from the circuit. And what that does, it causes the resonator frequency to shift. And by doing that, we can back out what this G factor is, and we extract that, it's about 60 megahertz. That's kind of the coupling strength. And we do this for all the devices on the chip, and we do this for many other chips. Okay. Then what we do is we say, well, how do those map? How do these effective Hamiltonian parameters map to actually circuit parameters? Well, there's these analytical expressions for them that you can derive from the theory of transmons. You can say, okay, the resonator, linear resonator, has an inductive energy EL, determined by the size of the inductor, capacitive energy EC, determined by the size of the capacitor, and this is the resonant frequency that you get. Now, what's the inductor and capacitor for some distributed element resonator? Okay, there's formulas for that. It's microwave engineering, but you can go back and find them. The Qubit is similar, except you replace the inductor with the Josephson junction, and you have this inharmonicity term. The inharmonicity is roughly the capacitive energy. The coupling is roughly given by this expression here. These are all kind of approximate, except maybe for the one on top. They're derived in particular limits. In particular, they're derived in the limit where EGA over EC is very, very large. And may not be exactly correct. So really what you want to do is go and instead of doing these analytical expressions, do exact numerical ones. For that, we use SC qubits, which is this fantastic software package that was developed by Jens Koch group. He's at Northwestern, where I believe our hosts. This is a really nice open source package that lets you do all this circuit simulation and circuit analysis. And it was really the inspiration for a lot of the stuff we're doing here with this open source design project. Jens is now a collaborator, and really he's just a super nice guy. He's an angel. Can't say enough good things. So we go and we say, what can we learn by doing all this process? So can I actually just get a show of hands, like just use the raise hand or thumbs up or something reaction? How many of you have done any kind of electromagnetic simulation before? In particular, how many of you have used like EPR analysis through Qiskit? Okay, a few people. EPR analysis is known as energy participation ratio analysis. It's a way of figuring out how a device is going to behave based on the amount of electric field energy and magnetic field energy that's contained in the junction on resonance. And it's a really good theory. It was developed by Zlatko Minev, who is the sort of creator of Qiskit metal, actually former lab mate. Zlatko's fantastic. He's a brilliant guy. The theory works great. It's really terrific, but it's vulnerable to inaccurate simulation. In particular, it's going to depend on how accurately you can simulate the field at the Josephson junction, which is typically the smallest thing on your entire circuit. And it's possible to actually miss pretty widely on that field without missing very much on things like the frequencies of your resonant modes. And those frequencies are typically what your simulation is actually looking at to determine whether it's converged. So your simulation will think it's converged, but it hasn't actually converged in the junction field. And this can really make you miss. So as an example, on the left here is an actual picture of a physical device that we made. A little bit of false coloring here to show the squid loop here. This is the cross from a tunable transmon with some coupling capacitors next to it. This is what our initial simulations said would work. And it was about 2 orders of magnitude off on the coupling. On the right here is what actually ended up working. In particular, this capacitor is much smaller. This coupling capacitor is way, way stronger. This coupling capacitor is a good bit stronger. So you really have to be careful here. So we've mostly gone away from EPR analysis. On the other hand, changing our circuits into lumped element equivalent models has worked surprisingly well. Even if we have distributed elements, there's sort of lumped element equivalents that work for those. And this has really been quite scalable and relatively accurate. For those of you who are familiar with it, don't use the rotating wave approximation if you want to do anything correct with device design. If you go and look at the literature, you'll remember this Lamb shift that I talked about. This was, how much the resonator frequency shifts when you remove the qubit from the circuit, or when you add the qubit to the circuit. And pretty much everything you'll see in the literature says a G squared over delta, the difference between the qubit frequency and the resonator frequency. Well, that's only right if you actually throw away a couple of terms in what's called this rotating wave approximation. The actual value is this. Not including the second term made us miss by close to a factor of 2 on our extraction of G, which really confused us for a while. So you just got to be careful. You got to include all the terms in your Hamiltonian. Throw them away at the end if you're sure they don't matter. Another thing we found out is that the line width of a resonator, sort of like how broadband its resonance is just not something you're going to be able to predict to super close accuracy because your microwave environment is going to have impedance variations as a function of frequency, and those are just going to mess with the line width in a way that has nothing to do with your design. So going through all this, what actually works? Well, the way these things, these simulations work is that they break space up into a discrete mesh. And they turn the differential equations, Maxwell's equations, into discrete difference equations, which can then be solved. Now you need to mesh very, very finely. You know, the system basically needs to be able to figure out that things have a gradient so that it can say, oh, wait, there's something changing here. I need to divide that into finer elements. So you have to mesh very fine, but not too fine, because if you go too fine, then you overwhelm your memory and your simulation crashes. So there's adaptive meshing in all these programs. It sort of refines itself as it repeats over and over, but it needs a seed. It needs to start fine enough. And so what we found is that any geometric element, say like this coupling capacitor right here, needs to have at least 3 meshed elements across it at the start. And what those 3 mesh elements do is it lets it sort of notice that there's a difference between the edges, which are these 2, and the middle, which is one in the middle. And when it sees that gradient, then it notices, okay, I need to divide these up more finely, and it seems to figure it out and converge. There's also this question of when do you consider a simulation to be done? And typically the way this works is it says, okay, I'm looking at some parameter, for instance, mode frequency, and I'm repeating this difference equation solution over and over and over, refining the mesh every time. And the convergence is when sort of the answer stops changing when I refine things. Well, okay, stops changing by how much? The default value is usually 0.2%. That's not good enough. We found 0.05% usually is good enough. Again, the more you turn it down, the finer tolerance you require, the better your simulation is going to be, but it takes a lot longer. Likewise, you can sometimes get kind of a fake convergence. You know, it thinks it has gone from, it refined a mesh and it redid the solution. And from one iteration to the next, it didn't really change very much. But that's just because it refined the mesh in the wrong place. So sometimes it has kind of a fake convergence. And so what you need to do is tell it, okay, but do another round and do another round after that. And only if you get 3 in a row that are good, then you can consider yourself to be converged. Now, okay, these numbers are just sort of empirically what seemed to work. So let me show you this. So what I'm showing is the simulated resonator line width. This is kind of the hardest thing to simulate. As a function of how many passes, how many iterations we required it to be converged in a row before we considered it to actually be converged. And as a question of this tolerance parameter in percent. So can't maybe quite see here, but this star symbol right there and that star symbol right there, those are the values we actually used. Now, what you can see is that as we turn up the number of converged passes, it sort of like was at one value, and then it comes up to another value. Now, the actual true answer was up here. This was a measured device. But as I said, we always just miss by some systematic amount on this kappa. So really what we're looking for here is just this saturation. Now, okay, you can say here it maybe isn't fully saturated. Here it's much more saturated. But the color here is indicating how much time the simulation took. This one over here took about an hour and a half. This one took about 5 hours. If I go all the way over here, it took almost 13 hours. Likewise, as we decrease the tolerance, okay, it's down here, and then it sort of jumps up and really hit the right value. And, again, that took about an hour and a half. If we keep decreasing the tolerance, we get up into sort of like the 10, 15-hour range. And so this is kind of the best compromise that we can find. There's something about the order of the solution. This is sort of a fine detail. Basically, each mesh element here is represented with a polynomial describing its field strength. And that can be either a constant, a linear function, or a quadratic function. And you can either say, okay, all of them are the constants, all of them are linear, all of them are quadratic, or you can allow them to be different depending on which element it's talking about. That's this mixed order. That seems to work best. We're not exactly sure why. In general, the smaller the thing you simulate, the better, because the convergence is going to happen much, much faster, which means you can turn up your accuracy parameters. And you got to be really careful. You just got to make sure that everything that you're simulating really looks like what you're actually making. So for instance, one thing that happens quite often is we have these pads where people wire bond onto the chip. So it's just like kind of a big square. Actually, if I can jump back, I'll show you what it looks like. Yeah. So that's like this little feature down here. And that's where we attach wires to get onto the chip. Well, that's a big hunk of metal. And if you don't include that, then you might get the wrong value for some coupling. Likewise, we have these air bridge crossovers that connect one side of a ground plane to the other without touching the thing in between. If you don't include those and you don't make them the right height and the right density, then you might get the wrong answer. Often when you do these simulations, you can say, okay, my substrate is silicon. It says, cool, the dielectric constant of silicon is 11.9. Well, that's at room temperature. When it's cryogenic, it's 11.45. You got to make sure you use the right one. You just got to sort of check through and be careful. Okay. Having done all this, we built squats, the superconducting quantum, superconducting qubit and device design and simulation database, where we did what I was talking about. We took this validated design and simulation workflow. We made a bunch of different devices in design space. We simulated them to map them to Hamiltonian space. And then what we say is, okay, now you're allowed to pick a point in Hamiltonian space and we'll map it back for you. This has a front-end API. The idea is just that this sort of queries this database of designs for you. It does the mapping between effective Hamiltonian and actual circuit parameter Hamiltonian then to design space. Can also let you simulate things. It can let you interpolate between designs that haven't been made yet, and even contribute your own designs. Now, I believe a bunch of you are going to be working on a squad project, and so we welcome your contributions. Here's how it looks, and Shanto is going to go through all this in much more detail for you next week, and really, he's the person to ask about all this. So first, you just connect to the database, and literally you can just import the database. Just do a pip install and then import it. Then you say, select what your system is going to look like. So in this case, it's going to be a cross-style qubit with a claw-style capacitor coupling to a cavity like this. That cavity is going to be a rep meander type cavity, so it's just meandering resonator, which at the end is going to couple to a transmission line with what's called a coupled line T, just sort of two co-propagating transmission lines. Then what Squaz does is it says, okay, well, let me merge that into an actual complete design, not just two separate things. And choose, then what you do is you choose, okay, here's the Hamiltonian I want. I want a qubit at 4 gigahertz. I want a cavity at 6.2 gigahertz. I want a cavity line width of 120 kilohertz, quarter wave cavity, 200 megahertz anharmonicity in the qubit, et cetera, et cetera. And it goes and it queries the database and sort of finds the closest design, where the closest is defined by some metric. Here, what we're saying is just sort of Euclidean space. It's basically the mean square percentage difference of all of these. You can define your own metric if you want. And then it gives you the GDS file. So you actually get out this file. So that code I was just showing actually generates this. Now, okay, these bond pads are way too close, but that's a detail that you can fix later because maybe you want a different size chip. Now, one thing we tried to do is make it possible to interpolate designs. And what I mean by that is here's a map of sort of parameter space that we have simulated already, and this exists in the squad database. So here's G, coupling strength, alpha, and harmonicity. All of these points are a particular design. There's a cavity frequency and cavity line width. Every point here is a particular design. And then we say, okay, my target point is that little X right there. And you notice it doesn't land on any device. Well, there's a closest device. There's one that we have simulated. It's reasonably close. And so we give you that. And we say, here's the best one that we've already simulated. But maybe you want to be closer than that. Well, to get there, we need to do some kind of interpolation. Now, we came up with this way to do interpolation based on the physics of the device. This was about a week of work by me. And it looks like this, and all I want to say is that it's really complicated. It's really complicated, and it doesn't scale very well. This does not work for any other type of device, but it does work here. We have some target point here. The closest device design was here. Again, these points on the left and right graph are actually the same device. It's just two different parts of the design space, or the Hamiltonian space that we're looking at. When we interpolate, we get a lot closer. We do that with another device, another one, another one, another one. And they all look pretty good, except for this one, where the interpolation actually made it worse. And that was a case where the target was kind of far outside where we had already simulated. So it's kind of far away. It was in a sparse region. Now, we'd love this to be more arbitrary. We'd love this to work on a different type of design than the one we already have in there. And I've tried to figure out a way to do this just using the physics, and it's very, very, very hard. And maybe someone smarter than me can do it, but I've decided that I can't do it. Probably a better way to do it is some kind of machine learning algorithm. We just have a mapping from this space to this space, and we want the inverse map, but we don't know what either map is. That's a perfect use case for machine learning. That's exactly what it's really good at. So this is one of the possible projects for you. So let me just say sort of where we stand right now. Right now, we only have data on a couple types of devices, basically just the only things that have been measured in my lab. We need to add more. This is one of your possible projects. Right now, the devices have to be drawn in Qiskit metal, and they have to be simulated in ANSYS HFSS. Qiskit metal is great, but maybe you use something else. ANSYS is really powerful, but it's also very expensive. We'd love to go to a open source thing. So one thing we're working on now is integrating support for AWS Palace, which is open source. And I think we've pretty much got it working. Unfortunately, Palace just doesn't work as well as HFSS. Its mesh refinement algorithm isn't as good. Needs improvement. Maybe something you want to work on. We're trying to make it so that users can actually create truly arbitrary circuits. Not just something that looks like a design that's been put in, but something that combines different pieces of all types of different designs and just smashes them together. And man, is that proving to be a difficult scientific question. So this is probably going to be a multi-year research project. We're working on these machine learning interpolation schemes. We've got some simple ones running. Maybe you want to make some fancier ones. And in general, we're just looking for user feedback, and we're looking for contributions. So that's all I have for now. I'll take questions. I do want to mention I am hiring postdocs. Got the paper for this. You can just look at the archive. It's actually published in Quantum now. And you can look at the project, the database, and the documentations here. So thank you. I'll take your questions.
Thank you so much for your wonderful lecture. I'm sure everyone else, including me, we've all learned a lot. So we have a bunch of questions. I'll get to them now. So the first question is, in your design process, how much do the available resources in your own lab or clean rooms influence your choices? For example, if you aim to create a SIS junction with a thickness of 50 nanometers, but lack the equipment to produce this consistently, how do you proceed? Do you partner with other classrooms or attend multiple samples or just revise the design?
So that's an excellent question, and that's something I hadn't discussed here because that's a major consideration. And the answer is kind of all of the above. So we put in a lot of work and a lot of money to making sure that we can fabricate what we need in-house. But also there's some things we can't do. For instance, in-house, we do not have a process for making these air bridge crossovers. So either we design things that don't need them, or we work with collaborators who can make them. So in particular, MIT Lincoln Lab has this fantastic program where they act as a device foundry. And they get funding for it, which means we don't have to pay for it, which is awesome. We send them designs, they send us devices. The only problem with that program is just that it's a little bit slow on the turnaround. So it's not very good for device development. We do that in-house, and then we send out the final design to them. I will say that's the direction the field is moving, to this sort of foundry model. And so it is getting easier to get devices made, provided you have the right design. And that's kind of the whole reason we're doing this.
Okay, wonderful. Thank you for the comprehensive answer. The second question is, do you have any recommendations for literature or links to simulations for understanding how electromagnetic simulations are typically done?
Yes. Let me go find them because I don't have them on hand. There's a nice reference for how to do HFSS simulations. There actually, as far as I can tell, is not any good reference for how to do this in general in superconducting qubits. And I'm writing one. And hopefully it'll be in the archive within a month or so.
Okay, that's great news. And yeah, please share the links with us and we'll share it with the participants through Discord. Okay, the third question is, have you explored using surrogate modeling to map the design space to Hamiltonian spaces as a way to overcome the limitations of brute force methods?
Okay, I'm not totally familiar with the term surrogate modeling, but I'm guessing this is some kind of machine learning approach.
I suppose so.
Yeah. Yes, we're absolutely doing this. This is something also we want you to do. But in particular, Shanto has some initial models where you can kind of get nice, easily trained machine learning models if you know some of the physics ahead of time. You can have a little bit of a physics-inspired model where you tell it, I'm pretty sure that this parameter is really going to strongly affect this parameter. And I'm also pretty sure it's not going to affect this parameter. And this sort of boosts the model along its way and can help train it a lot faster.
Wonderful. So this is like a way of, I think, contributing to the field. So I suppose it's like a developing topic, I guess. So yeah.
Yes. And we absolutely want people to take this Hugging Face database and just have at it. We want people, there's a reason we do this all publicly. We want more people to work on it.
Okay, wonderful. So that's a great lead. The fourth question is, how important is identifying the gradient when refining the mesh? Could you explain the reasoning behind the minimum requirement of 3 features for this process?
Yes. So first, let me say, some of this is supposition and inference because ANSYS, the company, hides how they do their mesh refinement algorithm. That's their secret sauce. That's their intellectual property. But in general, what it says, the way it works is, okay, it starts with some mesh and it solves Maxwell's equations as a difference equation on that mesh. You can just sort of iteratively work your way through by just guessing a solution. And what it finds is there will be, mesh elements where things changed quite a lot from one side to the other. And if things are changing quite a lot from one side to the other, it says, well, there might be something going on in the middle too. Let me divide that mesh element up. And I believe it probably divides it into more pieces depending on how steep that gradient was. The challenge can be, what if you have kind of a local minimum or a local maximum? What if you have something that's kind of sharply changing, but then turns around? If your mesh element spans that whole space, it can actually look like it's constant on either side. And so it doesn't look like it's changed at all. Now, typically this happens sort of between the edges of a feature and the center of a feature. The edges are typically kind of similar fields, and the center is typically kind of a different field. And so you kind of need to notice the difference across it. 2 elements nominally should be enough, but for some reason it never seems to work. 3 usually works. And that's just a seed. It goes from there and then it refines automatically.
Oh, that's interesting. Okay, thank you. And the last question that I have here is, it has been said that a smaller circuit is better because the simulation is faster. But if the circuit is small, don't we need a finer mesh? And furthermore, don't we increase the risk of non-convergence?
What I mean by small is not that each individual feature is smaller. I mean that rather than looking at, an entire chip that has, let's say, 10 coupled qubits on it with 15 resonators and I don't know, 18, I believe, tunable couplers, look at one of them. Just go and shrink it down to a subcircuit. Define things as small as you can, as limited of a circuit as you can, and simulate just that part. Then turn it into an effective lumped model. Because these effective lumped models can be solved very, very quickly, and build those up. So whenever we can, basically, the whole power behind squads, I would say, is the fact that we've been able to divide up our devices this way. Because what that lets us do is, simulate 1,000 of this part and 1,000 of this part and get 1,000,000 devices, rather than having to simulate 1,000,000 of these together.
I see. Thank you for the clarification. We do have a little bit more time. I'll be looking out for more questions, but thank you so much for your expertise here and answering the questions. I'm sure everyone is super happy to be learning from an expert like yourself. I invite my other core organizers if they have seen more questions that we can ask.
Yeah, there's one question. How do you account for environmental interaction in the simulation of the Hamiltonian? What techniques are commonly used to model these effects, and how do they impact the accuracy of simulation?
Yeah, so I didn't quite get into this. There's a couple things you want to look at. One is just coupling to external microwave feed lines. So I was talking about the cavity line width. What we do there is we write out we make the resonator structure, and we also make a little bit of the structure of the feed line that it couples to. And we tell the simulator, okay, end that in like 50 ohm resistors, and we're not gonna care about where those come from. That's just the 50 ohm microwave environment. And then you can do a simulation that'll tell you the quality factor of the resonance, which basically gives you the line width and lifetime. You can do the same thing for a qubit, and in particular for a transmon, it's a really good model. Where now the thing you're concerned with is, say, drive lines that come in and couple to the qubit. You got to give those a 50 ohm termination and see how that affects the qubit lifetime. So that's one thing. Another thing that can be important, which we haven't done at all in squads, is to simulate the effect of lossy materials. So in particular, the interfaces between the substrate and the air, the substrate and the superconductor, and the superconductor and the air, all those interfaces seem to be quite lossy. They basically, if electric field goes through them, they absorb some energy. And you can explicitly include that in your simulations, and this will sort of tell you how much loss you expect. And in fact, a lot of qubit design goes into making sure that those lossy layers have as little electric field in them as possible. We are hopefully about to start, depending on how well a grant proposal goes, about to start a project with some collaborators where we're going to get into this in much more detail and really incorporate this much more finely. But it's a difficult problem. There's one other thing to be concerned with, which is sort of lowish frequency noise coupling in. In particular, if you have a squid, if you have something that's flux tunable, there will be flux noise, and that noise will affect the qubit frequency and therefore will reduce its coherence. In SC qubits, there's a way to sort of, model that flux noise going in there. So this is something you can do at the sort of circuit level or even at the effective Hamiltonian level. For that kind of thing, it's typically not something you would want to do at the electromagnetic simulation.
Thank you so much for this wonderful answer, sir.
And I think we have time for one more question. And the question is, how do you account for environmental interactions like TLC in the simulation of the Hamiltonian? What techniques are commonly used to model these effects, and how do they impact the accuracy of the simulation?
Yeah, so I think maybe you mean TLS, two-level systems, or two-level couplings, I guess was TLC. Yeah, these are these lossy dielectrics that I was talking about. The issue that we run into is what's going on in these dielectrics is that there's this sort of distribution of two-level systems, and we call them two-level systems because all we know about them is they seem to have a couple of levels that are split near the qubit energy. That's it. And there's sort of a distribution of exactly what that energy splitting is for them, and there's a distribution of how strongly they couple to the qubit. Sometimes you get kind of unlucky, and there's a few of them that are close to your qubit frequency and coupling kind of strongly. And that can really limit the qubit lifetime. Sometimes you get lucky, and there's very few of them. But in general, it's sort of probabilistic distribution. I mean, we could do some random probability distribution in there and try to include that, but it's generally what we're concerned with is, on average, how is the device going to behave? So we just include an average loss density. And you can really model that classically as a lossy dielectric. So we model this as a lossy dielectric, and then we say, okay, given that there's this lossy dielectric and that the qubit is kind of a resonator mode, what does it look like? What is the quality factor as limited by that loss? How does the energy lifetime decay?
Thank you so much, Professor Eli. Maybe we'll take just one last question and then we'll wrap it up. You mentioned that superconducting transmon is weakly enharmonic. Is it possible to engineer it to more strongly enharmonic, or is there some advantage to being weakly enharmonic?
Yeah, so there's just by itself, there's basically no advantage to being weakly enharmonic unless you want to use the higher levels for something. So you can use them as a Q trit or a Q dit, use 3, 4, or 5 levels. But if you're just trying to get a Q bit, it's really a problem that it's weakly enharmonic because the enharmonicity basically sets a speed limit on how fast you can drive anything. If you decrease the junction energy and increase the capacitive energy by decreasing the size of the capacitor, then you get more enharmonicity. In particular, the enharmonicity is basically equal to the capacitive energy. However, at some point, as you decrease the capacitive energy, you start becoming more and more sensitive to the local electric charge environment. Basically, the frequency of the qubit, the energy level splitting, starts to become sensitive to DC electric fields. And those DC electric fields can change kind of randomly a lot. There's just a lot of charge noise in these things at low frequency, and we've tried to get rid of it, and we really can't. So those were actually kind of some of the first qubits made, were these charge qubits, which had enormous enharmonicity, but they also had really short coherence times. And the transmon was a way to improve the coherence by making it insensitive to this charge noise without getting rid of all of the enharmonicity. And so it's a compromise. Now, there's another popular type of qubit that's coming. It's a little newer, but it's not caught on quite as much, but it is having some buy-in. It's called a fluxonium. And it's really got a different type of resonant mode. But in particular, at DC, there's actually kind of a short across the junction. So charge can just kind of redistribute itself. And it's insensitive to these DC fields, and it has a really high harmonicity. Unfortunately, it actually has a very low qubit frequency. Transmon qubit frequency is about 4 gigahertz. Fluxonium can be down to like 100 megahertz. And that just makes it harder to drive it fast. There's work on this. There's some really impressive results out of Will Oliver's group at MIT recently. But it's always kind of a trade-off. We'd love to have a more enharmonic transmon. People are trying to figure out ways to have a more enharmonic transmon, but no one's yet figured out how to do it without making it less coherent.
Wonderful. Thank you for the answer to this wonderful question. And yeah, I think that's all the time that we have. And thank you so much for your lecture. Everyone, we only had this lecture today. So thank you for joining us. And we have recorded the session and we will upload it on YouTube. So you can find the link on the Discord after the session. And make sure to tune in tomorrow and the rest of the sessions. And if you don't have the calendar, like we created a calendar with all the information about the timing and the name of the session. So make sure you find that if you haven't already. Yeah, and I'll see you on Discord and other sessions. Thank you, everyone. Hope you have a good rest of your day, wherever you are. Bye-bye.
Thanks, everybody.